last lecture, we looked at the mathematical solution of the response of a single degree of freedom system to harmonic loading. And the specific harmonic loading that we looked at is P naught sin omega bar t. Okay. I would like to start off this lecture and this is actually a continuation of response of SDOF structure to harmonic loading. So, what we did was, in the end we saw that for a damped system the response u of t is equal to e to the power of minus zeta omega t C1 sin omega dt plus C2 cosine omega dt plus P naught upon k into 1 minus beta squared the whole squared plus 2 zeta beta the whole squared inside 1 minus beta squared sin omega bar t minus 2 zeta beta cosine omega bar t. Okay. This was the solution that we obtained. Now, what does this solution contain? I mean, and as I said, the C1 and C2 can be obtained from the fact that initial conditions. Okay. No, but so therefore, I am not still solved the entire thing, but the essence, let us look at what this looks at. There are two parts to this problem. This is the homogeneous part. In the homogeneous part, if you look at it, what does the homogeneous part depend on? It depends on omega and zeta. Okay. Those are the two quantities that determine this part. And if you look at this part, what does this part depend on? This part depends on P naught by k, which is the equivalent static peak displacement. P naught upon k, remember P naught upon k is P naught is the peak amplitude. So, P naught upon k is the peak equivalent static. Okay. So, that gives you the static response, but the dynamic part depends on two terms. One term is xi, which is the damping ratio, and the other important parameter that it depends on is beta. Beta is the frequency ratio. It is the ratio of the excitation frequency to the natural frequency of the structure. So, in other words, if you look at it, again it boils down that the response of a single degree of freedom system depends on zeta and omega, which are the dynamic characteristics of the structure, which we talked about in the 2 lectures ago, and the other part that depends on is the ratio of the excitation frequency to the natural frequency. So, in other words, 3 parameters define xi, the damping ratio, omega, the natural frequency, and omega bar, the excitation frequency. These 3 parameters define the entire response of the single degree of freedom to harmonic response. The other interesting part, if we look at this, is the following. You see, C1 and C2 depend on the initial conditions, but if you look at this part, what is happening to this part? This part is a harmonic excitation, sorry, a harmonic should I say part which is modulated by e to the power of xi omega bar t. So, let me put it this way, that if we look at a sufficiently far away time from the initial condition, right. If you look far away, what is going to happen to this part? This part is going to diminish and it is going to go to 0 because of this term. And so, this term is going to disappear after a sufficiently long window. How long that window depends on what this xi is. If xi is small, this window is large. If xi is large, this window is small. It does not matter. The fact remains that this part is dissipated and what you are left with is this part. Now, what is this part? This mathematically is a particular solution. Physically, this part is called as the steady state response. Why is this a steady state? That is that, as I said, this part comes from the initial conditions. Now, if you take a sufficient window of time away from the initial conditions, then this is what is remained. So, this is what is known as steady state. In the steady state, once the transient is damps out, the steady state response is what remains. And typically it is seen that by and large, although we look at it from this perspective that look, this part does look at the initial conditions, but if you look at harmonic excitation, harmonic loading, when do you have harmonic loading? Remember that when you start a rotating machinery, you start it from a particular RPM and then you build it up to a particular RPM, and then at that RPM, okay, you look at that response. And so, the actual, if you really look at it, our time that we start looking at is really just a snapshot. Actually, the loading has lasted forever and it continues. This is not drawn very well, it is actually a harmonic load. But the point is that there is no initial condition. I mean, the initial conditions actually happens at, let us say, minus infinity. So, when you look at response, then all that you get is the steady state response that we are interested in. So, this is ultimately the response that, however, note one thing, that if you had no damping, this would never get damped out, and that, in other words, you would never be able to damp out the transient part. However, even if you have very low damping, at some point of time that transient part will be damped out and you are left with steady state. So, although undamped system does not have steady state, but you can take a situation where xi tends to infinity, tends to 0 without it being undamped. Do you understand my point? In that situation, you can define a steady state. The transient will go out, and if this loading has been going on for long enough, we can say that look, we do not care about the transient and we are left with the steady state response. And which is why in harmonic loads, because the load is supposed to be there forever, the initial conditions are part of the transient is eliminated. Even if you have slight damping, very small damping in the system, it is eliminated, and what you are left with is the steady state response. And therefore, the steady state response takes up a large role in determining harmonic response to single degree of freedom response to harmonic excitation. That is, in other words, this is true as long as xi is greater than 0. It cannot be 0. Steady state response makes sense, and steady state response is given in this form. So, I will call this now steady state response, 1 minus beta squared sine omega bar t minus 2 zeta cosine omega bar t. Okay. And if you look at this, see, this is sine omega bar t cosine omega bar t. So, this system can be written as square root of 1 minus beta squared square plus 2 zeta beta whole squared square root. It can be written as sine omega bar t minus theta. So, if you look at this, then this system, this equation can be written off in this fashion, and that is that it can be written as a sine wave itself. So, u s, and note that if you look at this squared plus this squared square root. Now, this one is already this squared plus this squared. So, if you put square root on the top, all that happens is it becomes square root at the bottom. Okay. So, u s of t becomes p naught upon k the square root into sine omega bar t minus theta, where theta is given by tan inverse of 2 zeta beta upon 1 minus beta squared. So, in other words, the steady state response of a structure to a loading given by P naught sine omega bar t, the steady state response is P naught upon k into this term sine omega bar t minus t. So, I can now say that, look, I will define a term d which I will take as 1 upon 1 minus beta squared the whole squared plus 2 zeta beta square root. If I define this, then I can define u s of t as d into P naught upon k sine omega bar t minus theta for a loading P of t P naught sine omega bar t, where d is given by this term and theta is given as tan inverse 2 zeta beta 1 minus beta squared. So, in other words, if we go back, what are we saying? We are saying that, look at this, if you have a loading P naught sine omega bar t, then the steady state response is d P naught upon k. Note that the amplitude of this is d into P naught upon k. Did you see this very interesting part? What is the peak steady state response become? D into P naught upon k. In other words, where d is given by a particular parameter. So, note that if I substitute in this parameter and get d, and I do a static analysis with d, I can actually get the peak response. You see the beauty of this. So, therefore, although we have done a lot of mathematics behind it now, and this the steady state lags it's minus theta, lags the load by a angle which is given by tan inverse 2 zeta beta upon 1 minus beta squared. Note that this theta, as zeta becomes very small, also becomes extremely small for almost all values of beta. Now, let us look at these two things. So this becomes a very trivial aspect now. That means U max is equal to d p naught upon k, where d is given by this term. Since steady state response, as I said, the transient response disappears, steady state response is what we are left with. Let us look at the two parameters. The two parameters that define the steady state response is d and theta. So, let us look at d and theta very carefully. So, therefore, d is known as the dynamic amplification factor. Obviously, why? Because U max is equal to d into p naught upon k. So, obviously, this is a static, and the U max to the dynamic load is given by d into p naught upon k. So, this is the dynamic amplification factor that gives us the peak load. Okay. And theta is called the phase lag of displacement response to load. In other words, what we are saying is that if there is damping, because note that theta is equal to tan inverse 2 zeta beta 1 minus beta squared. Okay. If there is damping, there is a phase lag. There is a positive phase lag. Note this. There is a positive phase lag of the displacement to the load. In other words, the load comes, the structure thinks for a while and then responds to it. Although this is not strictly true, because it is not really, the loading is not starting. We are looking at a particular point of time where the loading has been there for a while. The transient initial conditions, the transient part which was due to the initial conditions has been damped out, and all you are left with is the steady state part. And what we are saying is that the steady state part lags the load by a lag, phase lag given by this term. So, let us first look at delta. What does delta depend on? Let us look at both the terms, in fact. Dynamic amplification phase lag. So, I should now only talk about dynamic amplification phase lag from here on out. Okay. So, if we do that, so dynamic amplification is given by what do these terms depend on? These terms depend on zeta and beta. Beta is nothing but the frequency, excitation frequency to the natural excitation. These are the only two terms that these two things depend on. So, therefore, what we have is a situation where, if we look at this, the d, what does it look like? So, this d depends on beta. So, I will draw d with beta. So, on this axis I have beta, on this axis I have d. Let us see what d is. Let us start. And this plot I will do for a particular value of zeta. I will do it for a particular value of zeta. Let us see. Let us start. So, I am going to plot this, but before I plot this, let us see. Put beta equal to 0. put beta equal to 0. Plug in beta equal to 0, what do you get? You get this is 1 and this, if you put it as 0, this becomes 0. So, D is 1. So, D is 1 and note that D is 1 independent of xi. Okay? It is independent of xi. Now, what happens? Let us look at it. At beta equal to 1, what happens? At beta equal to 1, this term becomes 0, this term becomes 2 xi squared, square root. So, it becomes 1 upon 2 xi. So, at 1, the peak value is 1 upon 2 xi. Okay. Now, let us look at some large value, okay, large value of beta. What happens here when you start getting large values of beta? If you look at it, for large values of beta and small values of xi, remember that we are looking at structural damping, right? Structural damping, remember that xi is typically less than 10%. Which basically means xi is less than 0.1. Small values of xi, right? For very large values of beta, what happens is, look at this term. Let us take 100, beta equal to 100. Okay? So, what happens here? This becomes 100 squared. So, that is 10,000 minus 1. Who cares? You know, if you look at this term kind of completely goes over on this. And so, at very large, as beta tends to infinity, D goes down. If you look at this, this is very small. So, I can ignore this. So, this whole thing becomes 1 upon beta squared. Okay. So, in other words, here it goes down in a hyperbolic part. So, if you look at this, this is what it looks like. And here it goes down as almost 1 upon beta squared. Okay. So, in a sense, if we look at it, what are the key aspects? The key aspects is dynamic amplification at beta equal to infinity is 0. That is one thing that you see from here. Okay. So, that is very interesting. What does it say? That if you have, if omega bar upon omega is tends to 0, then beta tends to 1. If omega bar upon omega tends to infinity, beta tends to 0. Okay. And omega bar upon omega as it tends to 1, beta tends to 1 upon 2 xi. In fact, let us not say tends to, it is equal to 1, beta is equal to 1 upon 2 xi. These are interesting points, they are very interesting points here, and that is that what is omega bar upon? This implies static loading, because the dynamic, the omega bar is 0. In other words, the load, the excitation is not cyclic at all, it is in a kind of a constant P naught. And therefore, beta, sorry, this is not beta, this is D, D tends to 1. I am so sorry, I have made a mistake here. This D equals, D tends to 1. Well, if you have a static load, the dynamic amplification tends to 1. What does that mean? Well, all it means is that if you have a static load, there is no dynamic amplification. Well, it is a tautology, right. The more important thing is when the excitation frequency is exceedingly high relative to the natural frequency. Remember that. You see, this is all relative, omega bar upon omega. So, if omega, let us say, is 0.1 hertz, then omega bar, which is 5 hertz or even 1 hertz. Okay. Now, you would say that omega bar 1 hertz is not a very high frequency, but relative to the flexible structure, because 0.1 hertz is a 10-second time period, it is a very, very flexible structure. So, if you have a very flexible structure, okay, a 1 hertz loading, so if you have a 10-second structure and if you have a 1 hertz loading, what do you have? D tends to 0. Whereas, let us say if you have a 1 hertz structure, a 1 hertz structure, omega bar 1 hertz is resonance. Okay. So, however, it is always relative. So, when the excitation frequency is very high relative to the natural frequency, then the dynamic amplification factor is 0. What does that mean? There is no response. That is very interesting, isn't it? There is a loading, but there is no response. Okay? We will come to this. I will explain the physical aspect to this shortly. And that is that, and let us look at the other situation where you have resonance. What is D? 1 upon 2 xi. Think of xi typically in a structure is in the 2 to 5%. That means take 2% here. What do you get? 1 upon 0.04, 25. Okay. So, for a 2% structure, dynamic amplification at resonance is 25. For 5%, it is 10, still very large. So, therefore, at resonance you have large amplification of response for harmonic loads, for any kind of normal structure. As I said, normal structures, the damping is always less than 10%, and so you have that. Now, let us try to look at these two aspects and let us see what these mean, because this has a physical relevance to what I have talked about earlier, and that is, let us see. Relative to the structure. This is actually T bar by 2. This is half cycle. So, it is T bar by 2. Okay. So, if you have omega bar upon omega tending to 0, it basically means that as far as the structure is concerned, this load is a very, very slowly varying load, a very slowly varying load. If it is a very slowly varying load, okay, what happens? For all practical purposes, if we look at it, let's substitute this in. So, let us see what dynamic amplification is tends to 1, and let us look at what happens to theta. It will be instructive to look at theta. I was not going to look at theta right now, but let us instructive. Theta is tan inverse of 2 zeta beta, 2 xi beta 1 minus beta squared. Now, beta is equal to 0. So, this becomes 1 and this becomes 0. Tan inverse of 0 is 0. So, theta is 0. That means what? There is no phase lag. So, when you have a very, very slowly varying load, how does the response go? The response follows. So, when it is a very slowly varying load, okay, the response, there is no phase lag, it follows exactly what it is, and of course, this is P naught upon k, where this is this is P naught. So, we are actually plotting it in two different scales, but the point that I am trying to make is that for a slowly varying load, as far as the structure is concerned, it is being subjected to a static load. So, if the excitation frequency is very low compared to the natural frequency of the structure, you can, for all practical purposes, not have to do any dynamic analysis, because what's the peak response? P naught upon K. You might as well do a static analysis for the load amplitude P naught. Okay. Very important. Now, this can actually be extended to all kinds of loads. All kinds of loads is later on, I will discuss it further. If you look at loading frequencies, we will see later on that loading frequencies, and we will have a central loading frequency. These are terms. So, if you look at the central loading frequency, you can obtain this by performing some mathematical operations on load. If this is very small compared to the natural frequency of the structure, you can do static analysis for peak response. Very, very important. If the loading frequency, and I mean in this particular case it is a harmonic load, so we know what the loading frequency is. But for any kind of loading, by performing some mathematical operations, you can get the central loading frequency. The loading frequencies in which the maximum energy of the load is. Once you do that, and if you look at those, and those are very less compared to the natural frequency of the structure. Okay. So, you have a very rigid structure. If you have a very rigid structure, any loading is going to be a static load for the rigid structure. So, in other words, if you have a very rigid structure, what can you say? You do not need to do dynamic analysis at all. You can just do static analysis and get away with it. Is that clear? Okay. So, that is the beauty of this approach. Okay. Now the question becomes, what happens as omega bar upon omega goes to infinity? We saw that dynamic amplification goes to 0. Why is that? Well, let us look at it. We just saw that for as omega bar upon omega tends to 0, it becomes a slowly varying load, and therefore, it is a static load as far as you are concerned. Okay. Now, what happens when you have omega bar upon omega tending to infinity? What happens when it is tending to infinity? When it tends to infinity, let us look at what happens. This is T, this is P of T, P naught minus P naught, P naught minus P naught. This is what is happening. I mean, I am not going to draw it, but what we are saying is that omega bar is excitation frequency is very high. Excitation is frequency is very high. What is the structure seeing? The variation is so fast, all the structure is actually seeing is a load P naught and another load minus P naught acting on it, because the time variation is so quick that as far as the structure is concerned, all it can see is the P naught and minus P naught. So, if you subject a structure to P naught and minus P naught, what is the response? As far as the structure is concerned, right, it is not seeing any load at all. because it's being subjected to two equal and opposite loads. So, if it's subject to two equal, the response, the displacement response of the structure is 0, and that is why D is equal to 0, not very obvious. It is very instructive to look at what happens to theta as beta tends to infinity. Okay. Theta is given by this term. As beta tends to infinity, note that this term disappears, right. So, what do you have? You have beta upon, so basically it becomes tan inverse of 2 xi upon minus beta, right. So, it becomes 2 xi upon minus beta. So, it becomes minus 2 xi upon beta, right. So, it is tan inverse of minus 0. Okay. Think about it, as beta tends to infinity, this tends to minus 0, this term. So, if it tends to minus 0, what is tan inverse of minus 0? Tan inverse of minus 0 is pi or 180 degrees. Interesting, isn't it? So, if I look at the load, I mean the load is very high, dynamic amplification goes to 0, but let us assume that it is not tending to infinity, it is slightly less than infinity. So, the load goes like this, and how does the response go? The response goes like this. Interesting, isn't it? Response, load. The load completely is out of phase. The response is completely out of phase with the load. Okay. Why is that? What's happening? What's happening? Now, let's also see what happens where you have beta equal to 1. We saw that D was equal to 1 upon 2 xi. What is theta equal to? Let's see. Let's plug in. Beta is equal to 1. So, this is 1, 1 minus 1 is 0, and this is 2 zeta upon 0. What is that? Tan inverse of infinity. What is tan inverse of infinity? If you look at tan inverse of infinity, it is pi over 2 or 90 degrees. What it means is that if this is the load, then the response is of the following type, where this is maximum, this is 0. So, response is of where this is maximum, this is 0 again. So, that is the response. It is 90 degrees out of phase with the loading. Okay. So, when it is extremely high, when it is extremely low, the response is in phase with the load because it is static. When beta is 1, which is resonance, okay, dynamic amplification is 1 upon 2 xi. In other words, it's extremely, the response is extremely large and it is 90 degrees out of phase. It's exactly out of phase. So, in other words, it's almost like being a sine omega bar t is the loading, then minus cosine omega bar t is my response. That is what it says, because it's that sine and cosine is 90 degrees out of phase with sine. So, if it's lag, the lag of sine omega bar t is minus cosine omega bar t. Okay. If it's extremely high frequency, dynamic amplification tends to 0 and response is completely out of phase with the loading. Now, this is what we get can we see, is there a physical, the mathematics tells us this, is there a physical aspect to this particular thing? And for this we need to go back to the fundamental aspect of what is US. US of t is rho sine omega bar t minus theta, right? That's this term. Of course, P naught is P of t is P naught sine omega bar t. Now, note that rho is equal to P naught upon k d. Okay. So, if I differentiate this, u dot s of t becomes rho omega bar cosine omega bar t minus theta. Okay. And if we look at it, u double dot is equal to minus rho omega squared sine omega bar t minus theta. This is what we get, I mean, you can see it very clearly. Okay. So, now let me on a complex plane plot these terms. Okay. So, let us look at this. Now, note that if I am going to plot it on a complex curve, these are all real quantities. Okay. So, what I am going to be plotting is I am going to plot a complex vector whose projection on the real axis represents this. Okay. So, that is what I am going to do. Please note that the vector by itself means nothing. The vector by itself does not represent anything. These are represented, the component on the real axis is what represents all these terms. Okay. So, let me now draw this thing, and what I am drawing now is known as the Argand diagram. Okay. Got to run the Argand diagram. And how does the Argand diagram look? Let us just plot it. So, this is the real axis, this is the imaginary axis. Now, I have a P naught sine omega bar t. How will that look? That looks like this. It looks like P naught. This is omega bar t. Let us look at this. Let us look at the real projection. Remember I said that it is always a real projection. So, let us take the real projection. What is the real projection of this? If this is omega bar t, okay, that means this is omega bar t, right. So, what is this term? This term is, if this is P naught, this is P naught, this from here to here is P naught. Okay. If this is P naught, then obviously this part is equal to P naught sine omega bar t. Remember, that is what it is. The load is given in the real axis, right. So, this is, so in other words, this vector in the complex plane represents P naught sine omega bar t, because its real projection is P naught omega bar t. In the same way, I am going to plot now the US of t. Let us see what this US of t is. It is given as P naught d upon k sine omega bar t minus theta. So, to represent this, I can actually plot it here. These are, I mean, this is not the, I am just plotting P naught. The P naught should be plotted on a force complex plane, and these should be the displacement complex plane. I am just drawing them on the same, axis. It does not really matter, where this represents theta, okay, and the amplitude is given by P naught upon k into d. Okay. So, this is your displacement. So, displacement is this direction. Okay. I mean, if you look at this, this is omega t minus theta, and if you take the same thing, you will see that this is indeed P naught d upon k. So, this is the displacement. This is P naught d omega bar upon k cosine. Now, how does cosine look? Cosine, if you look at it, it actually leads. Okay? It always leads. So, it is leading. See, this is lagging, this is leading. Let us plot this, and this one I am going to plot it in this direction. So, this is the direction of the displacement vector, this is the direction of the velocity vector. Okay. And what is the value of this? The value of this is P naught d upon k into omega bar. That is the velocity, and let us see whether this makes sense. Okay. Now, if this is omega bar and this is 90 degrees, which is my omega bar now. If you look at it, omega bar t, because this is omega bar t minus theta, and this is 90 degrees to it. So, which is my omega bar t minus theta? Let us see. This angle would be omega bar t minus theta, isn't it? And let us look at its real projection. Its real projection is equal to this parameter into cosine omega bar t minus theta. See, that is it. That is how it is. Okay. And if you look at this, this is just negative of sign. So, if you look at this, the acceleration is in this direction. The acceleration is in this direction. And what is the acceleration equal to? P naught d upon k omega bar square. So, this is my omega bar t minus theta, and you will again see that this is nothing but sine omega minus sine. So, this represents these three represent the displacement vector, the velocity vector, and the acceleration vector. And these, they are, this is in this direction, the velocity vector leads the displacement vector, and the acceleration vector is completely out of phase with the displacement vector, and these vectors with t keep rotating, and they are all 90 degrees to each other. Okay. So, this is a very important aspect. In the next lecture, I am going to carry on this to show you how the entire load is carried by the various forces. Okay. We are going to do force equilibrium, Argand diagram, and it will be going to be very interesting, because if you look at it, this is the displacement. Okay. So, elastic force opposes the displacement, the inertial force will oppose the acceleration, and the damping force will oppose the velocity. So, these are interesting points, and we will look at this in the next lecture. Thank you very much.